In this video, we consider the likelihood function for conditional models as well as time series models. Moreover, we define the maximum likelihood estimator and we introduce some convenient notation. In many applications within econometrics, we consider so-called conditional models. So, for instance, we want to say something about a variable yt given some variables xt. This could, for instance, be a linear regression model where yt is the left-hand variable and xt denotes the regressor variables. In this setting, we may not know the joint distribution of the y variables and the xt variables, but we may only come up with some assumption about the conditional distribution of yt given xt. So in particular, we may say that yt given xt has some distribution that by definition depends on xt and that depends on some parameters contained in theta. Here the likelihood contribution, Lt, as a function of theta, is simply the conditional density of yt given xt. If we now assume that the y variables are independent, conditional on the x variables, we can write down the log likelihood function as simply the sum of the log of the likelihood contributions. As such that the y variables may not necessarily be independent and they may not necessarily be identically distributed, but we assume in this kind of model here that conditional on xt we have this independence property and this property that the y variables are identically distributed. This is quite neat if you want to do, say, maximum likelihood estimation of linear regression models. In terms of time series, we typically do not have independence. Nonetheless, we can actually still write down the likelihood function. We just have to come up with some other approach than simply taking the product of the marginal densities. A classical time series model that we will analyze in detail in this course is the so-called autoregressive model of order 1. So it simply states that yt is given by theta times yt minus 1 plus epsilon t. Here clearly we can see that the observations must be dependent because by definition yt depends on yt minus 1. We may assume that the error term epsilon t is IID, and we typically consider the initial observation y1 as fixed. We can write down for any value of t what yt must be equal to. Note here in particular we do not have an equation for y1 because we simply take that observation as given, and hence we do not know what y0 is. That's not part of our data set. What is quite nice is that we can actually still write down the likelihood function in a convenient way. We will use again and again the following fact, namely that the joint density of y and x is simply given by the product of the conditional density of y given x times the marginal density of x. If we do that, we can actually factorize the joint density of the y variables in terms of conditional densities. So in particular, let us start out by considering the joint density of y1 up to yt. Then we can use that this is simply the conditional density of y capital T given the entire past times the joint density of the observations until time capital T minus 1. We can then factorize this second factor here into a conditional density and a joint density. Namely, we can state that joint density of y1 up to y capital T minus 1 is simply the conditional density of y capital T minus 1 times the joint density of the observations until time capital T minus 2. We can then do that recursively, and at the end of the day we end up by having that the joint density is simply the product from time t equal to 2 of the conditional densities times the marginal density of y1. But recall here that we think of y1 as given, so we essentially condition on this value. So what we can do is that we can write down the likelihood function as the joint density of the observations from time 2 until time capital T given our initial observation y1. And then by definition this is simply the product of the conditional densities from time 2 up to time capital T. So very convenient. So we get this product structure or multiplicative structure even though that the observations are dependent. This multiplicative structure is different in the sense that we are no longer taking the product of the marginal densities but of the conditional densities. We then have that the log likelihood function is simply the sum of the log likelihood contributions again, where the likelihood contribution is the conditional density. Let us next define the maximum likelihood estimator. So by definition, the maximum likelihood estimator is the argument that maximizes the log likelihood function over the entire parameter space. Sometimes we denote the maximum likelihood estimator theta hat capital T, or we simply leave out this subscript capital T and simply just denote the MLE as theta hat. Note here, if we consider the variables y1 up to y capital T as random, then we have that theta hat is the maximum likelihood estimator. But if we consider y1 up to y capital T as some data points that are realizations of the stochastic process, then we think of theta hat as an estimate. Next, we consider some convenient notation. The so-called score vector is simply the first derivative of the log likelihood function. Again, by definition, this gives us the sum of the first derivatives of the log likelihood contributions, and these first derivatives we may label as the so-called score contributions. Recall here that theta hat is the maximizer of the log likelihood function, so the first order condition for this maximization problem suggests that the score vector should be equal to 0 when we evaluate the score vector at theta hat. Again, note here that this score vector is a k-dimensional vector in the case where theta is k-dimensional. We may also consider the Hessian matrix, which is the second derivative of the log likelihood function. And again, if theta is k-dimensional, then the Hessian matrix is a k by k matrix. A quantity that we will use again and again in this course is the so-called Hessian contribution, which is simply the second derivative of a given log likelihood contribution. What shows up is that this Hessian contribution is closely related to the variance of the maximum likelihood estimator. More specifically, what we will use is the so-called information matrix, which is minus the expectation of the Hessian contribution. It shows up that this information matrix is directly related to the asymptotic variance of the maximum likelihood estimator. We've now defined the maximum likelihood estimator, and we said that this estimator is the argument that maximizes the log likelihood function. In some applications, we can actually find an analytical expression for the maximum likelihood estimator. So what we can do is that we can simply write down this first order condition and then simply solve this equation system here for theta hat. This, for instance, we can do for simple models such as a Poisson model or a linear regression model. But in more complicated settings, we cannot solve this first order condition. So what we can do instead is that we can simply do some kind of grid search. So we can simply choose some plausible values, say, of theta, and then try to figure out which one of these plausible values of theta gives us the largest value of the log likelihood function. That is very that is exactly what we did when we considered this toy example with the Gaussian variables in a previous video. Alternatively, we can consider some numerical optimization procedure, and we will get back to that later on in the course. But it shows up in particular when we consider nonlinear models. This is the way we want to optimize the log likelihood function. Thank you for watching this video.